Hello, everyone. It's really a great honor for me to introduce today's distinguished lecture speaker, Professor Christoph Brabec. First of all, I want to tell you a bit of how I knew Professor Brabec. I was still a graduate student at that time, and on organic solar cell, working on organic solar cell. One of the first papers we read, it was an APL paper. It was, at that time, the solar cell efficiency, I think, was at 2.5%. And solar cell was very tricky. The bulk heat junction organic solar cell was sort of invented in 1995. Alan Heger mixed a polymer with a fullerene. And for a long time, there was no progress. And one of the major milestones after Alan Heger's result was done by Professor Brabec. And then they used simply change a solvent and then change the morphology of organic solar cell. They achieved 2.5%. And that paper now today has been cited over, I would say, about 5,000 times. 5,000 times. Some papers in the entire field never got so many citations. And what's interesting, we were just discussing about that paper. In that paper, Professor Christoph Brabec said that the microstructure is very complicated. And we still believe it's complicated today. Okay, after 17 years, almost 17 years, the problems in OPV are still problems. Where efficiency-wise, we're much better today, but in terms of fundamental understanding, we're still working very hard. So at that time, actually, Professor Brabec was assistant professor at Kepler University in Linz. And then he went to industry and went to Siemens in Germany as a principal research scientist. And later, we all know that there was a famous OPV company, Konorka, and they have a branch in Austria, and then branching in close to Massachusetts. And so Konorka has been around for almost 15 years, and then after in 2009, Professor Brabec moved back to a university of in Erlangen-Nuremberg, and where he's currently a professor of material and science. And so I guess for people who understand OPV, I don't have to introduce Professor Brabec's work very much. But today I think we will hear more about the latest development in Professor Brabec's group, and not only about the efficiency, but also about the stability of organic solar cell. And now, without further ado, let's welcome Professor Brabec.
Thank you, Henry, for the very nice introduction. And yes, I'm pleased to be here. It's a wonderful opportunity. First time I'm to Hong Kong, and then I'm that lucky to really experience a typhoon here, so I'm very happy about this. We had no problems in flying in. So for today, I'm speaking mainly on stability and these microstructure issues. It is true that in the field of organic photovoltaics for more than 10-15 years, we are working on the microstructure, and we can observe microstructure, we can discuss microstructure, but we haven't resolved it, and we cannot predict microstructure. And today I will tell you a little bit about how to predict. Our first stage is to predict microstructure, and especially predicting in terms or in combination with what we call a materials genome initiative, which is a robot-based high-throughput experimental setup. Before doing this, let me highlight, because this is always one of the things which makes research so well possible and so strong in Germany, and this is the institution of group leaders or senior postdocs, which is most essential. So in my group, we have probably more than 45 PhD students on many different fields, and the only reason why this is possible is because here this series of group leaders is doing a fantastic job, and especially I'm highlighting Ning Li, who is here today, and Hans Egelhaar from the Solar Factory, and the ZA Bayern, who joined me on this trip. Let me explain a little bit also on the background and the funding. So most of the work we are doing is a mix between governmental funding, a little bit European funding, and then also industrial funding, and some of the industries which is carrying us for quite a long time. You might be familiar with Heraeus, who is developing or selling PDOT, but also companies like Cambrios, who is developing silver nanowires, or Durst, who is the world-leading manufacturer in inkjet printing. And I'll introduce you to the PhD students who actually were doing the work then when I come to their results. I'm going to introduce you to 3 different institutions which are connected very well and which allow us to do what we are doing. The one is the Friedrich Alexander University. This is the university in Erlangen. If you take a look here, this is Erlangen, this is Munich, we have Frankfurt somewhere here. So it's an hour by train from Munich. The distances look a little further, but there is this high-speed train, and within 1 hour you can go from Munich to Erlangen. Within 2 hours you can go from Frankfurt to Erlangen. It's a fairly large university for German aspects. We have more than 40,000 students, roughly 650 professors, and we cover all disciplines from technology, science, medicine, law, and humanitarian studies. The second institution I'm showing you, it's not necessarily an institution, but it's a major research initiative between 6 different institutions among the university, the Bavarian Governmental Institute for Energy Research, and then the Fraunhofer groups, and it's called the Energy Campus Nuremberg, ENCN. It's located in the west of Nuremberg. This is the area where formerly we had a major large facility electronic production. And roughly we are there like 30 professors in 6 or 5 different disciplines. And the research there is along the energy chain. So we try to bridge from the material to an application. And this is also the place in this building where Hans is operating the solar factory of the future, which is the printing institution. Formerly, the Solar Factory of the Future is a part of the Center for Applied Energy Research, and this is now the last institution I'm introducing to you. The Center for Applied Energy Research is located at 5 different locations in Bavaria. The one is in Munich, Garching at the Technical University. The site I'm heading is in Erlangen and Nuremberg, and Hof also, which is on renewable energy, mainly photovoltaics. Here we have energy storage, and here we have in Würzburg, it's located on energy efficiency. And these 3 institutions, renewable energy, energy efficiency, and energy storage, we are roughly 200 employees, like 60, 70, 80 employees in each of these main locations. And this institution is working very applied. So we are working almost exclusively for industry. And you see here the number of projects we are doing per year is in the year of 200 to 300 projects. And none of these projects is done without industry. So this is very applied. And if you take these 3 institutions together, the university, which is more on the fundamental side, the energy campus, where we do the process development, and then the ZAE, this Bavarian Research Institutes, we are able to bridge the fundamentals to the materials, to the process development, to the system development, to the application. We cannot do this for all types of photovoltaics, but we are definitely doing it for organic type of photovoltaics and for perovskite types. Where we have the expertise from here to here. And you can imagine the more we go advanced here, like here, then the more we start working on other materials, like here in the system approach. Most of our work is, of course, on silicon or CHS, but we are also in the progress of demonstrating outdoor stability or system approach of organic and perovskite modules. And in between, one of the very important parts here, this is in the ENCN, the solar factory Hans is operating. And in this solar factory, you see one of the main reasons why organic or printed photovoltaics is so interesting. This is a picture of a production line for organic solar cells or perovskite solar cells. The interesting thing is the same line can produce both types of technologies. And the other interesting point is the footprint. The size of this line is roughly like a 10 square meter. It's fairly long, but not that wide. So 10 square meter is enough to get a capacity to produce approximately 1 megawatt of photovoltaics. And that is amazing. If you would look to other technologies like silicon or CHS, in order to produce 1 megawatt, you need a full hall of hundreds of square meters. for production. And here, the major advantage of this technology is it's very cheap in production and it's very compact. Okay, so this for the introduction. Let me start a little bit with the motivation and the main challenges we are facing in the organic and printed photovoltaics, but also the roadmap. For the roadmap, the first thing you always would look at is the annual chart for efficiency. And just to give you orientation, these are all the material concepts for photovoltaics. And you can see we bridge a huge space in efficiency from the multiple junction cells under concentrated light, which are now at roughly 45 to 46% efficiency, all the way to the organic disorder, the quantum dot solar cells, which are in the order of 10% efficiency. This is the width of the space in research and development. If you look to the industry, then all of the industry is here. More than 90 or 95% of all solar cells installed are silicon. And then the next one to look at is here the thin film technologies. This is cadmium telluride and CHS. They are now at the level of 20% of efficiency. And then the amazing thing is you see here this very fast and rapid development. These are the perovskites, and the perovskites are also now at the same stage of efficiency of over 20, or almost 22%. So we have silicon, which is the market leader, but we have here at least 3 thin film technologies, and one among them is printed, which are at the same level of, this is monocrystalline silicon, this is here multicrystalline silicon. So the thin films are almost at the same level. And the last technology here, you can see this is organic and dye-sensitized solar cells, which are now at a 12.5%. And also still developing at a fairly rapid scale. And if we would discuss this in terms of semiconductors, you discuss disordered, multicrystalline, ordered semiconductors. The area here we are talking are disordered semiconductors. The area we are talking here is multicrystalline, and when we go up to the very high efficiency, we are talking about monocrystalline, epitactical grown semiconductors. So you can see that the efficiency kind of mimics or is following the quality of the semiconductor. And when you zoom in, you can see now the separate efficiencies for this very new and rising technologies. And you can see this is from June 2015. You can see here the statement from your university, from Henry Jahn, the 12.5%. And from the certificates, so just to make clear which numbers are coming on this efficiency chart, you have to get this efficiency measured from a certified institute. And normally it should be at a size of a square centimeter. But this chart is also accepting these notable exceptions where the cell size can be smaller. While when you go here, you typically have to be on a square centimeter size. So this is the area where we are looking at, and this is also where I'm talking today on the organic solar cells. If you wonder, if you ask what for which applications you may use these solar cells, we roughly distinguish, and I know this is never a harsh border, but we roughly distinguish in technologies which are over 10% efficient and over 10 years in lifetime. And please keep in mind, this is product. This is not a single cell, but this is a real outdoor product. And technologies which are beneath this. So this would be in the power application. And then we look at applications which have a small footprint or a smaller volume and a larger volume. And when we look to the classical, maybe before this, and the classical field of silicon is, of course, the power plants, the grid-connected greenfield power plants. This is where 95% or 98% of all the photovoltaics is going. But there are also these other applications which are currently niche applications like chargers, outdoor mobile, and now outdoor integrated and building integrated facades, which is getting very interested. And for the printed technologies, we roughly would estimate that perovskites, if we want to look for a printed technology for the greenfield grid-connected power plants, then currently perovskites seem to be very interesting. If you're looking to consumer electronics, mobile, then definitely it's organic photovoltaics, which is more interesting. And the very interesting thing is on the building integrated, that is actually a point where organic and perovskite might meet each other, and really we might see a very interesting and stimulating comparison between these two technologies. And of course, the question is, what is next? So what is coming after these technologies? And that is an open question. Let me conclude this very brief introduction to solar with two observations. And one observation is that solar energy by today, and that might be amazing to you, but it is the cheapest technology to produce energy. And how do you measure this? You see here an update from the last purchase order agreement for a 300 megawatt power plant in the United Emirates. And the cheapest costs there were 1.8 cents per kilowatt hour by a consortium from Masdar and EDF. So this means by solar energy, there are companies who believe they can produce electricity at 1.8 cents per kilowatt hour. If you compare this, at least in Europe, to other forms of energy production, nuclear energy is 15 cents, gas is 10 cents, coal is a little bit below 5 cents per kilowatt hour. Solar is 1.8 cents, so it's cheaper than any other technology. And the question is then, so why do we still burn coal and oil? So that is something you may think about. The answer is, of course, it has to do with industry and politics, but in terms of economy, it's an interesting question. Here's the second observation. Photovoltaics, we have now photovoltaics for more than 50 years. So people claim that 1954, this fantastic paper from the Shockley Group was the start of photovoltaics, where they had a 5% silicon cell. So it's more than 50 years or 60 years in research we have, and we're still looking very much into new materials, completely new materials. And as one of the examples I gave you here, the citation, when you go into Scopus and you just type in solution processed or printed photovoltaics, we have roughly 2,000 publications per year on novel materials for this printed photovoltaics. So there's a discrepancy in my point of view. On the one hand, we have a technology which is very major. It's a multi-billion-dollar business. On the other hand, one of the most active research communities ever is on new materials for photovoltaics, which reflects huge interest. So let me see if I can clarify some of this during the talk. And the scientific part I'm going to focus now is more on the microstructure and stabilities. And with this, let me just briefly summarize organic photovoltaics. I know many of you will be very familiar with this. For those who are more coming from inorganic semiconductors, organic photovoltaics has the speciality that you have to mix two semiconductors to get a functional device. And the reason for this is these are excitonic materials. And in order to split the exciton into free carriers, we need a second semiconductor. And the second semiconductor either has to be preferential p-type, the other one preferential n-type. So when light is coming in, we generate an exciton. The exciton has to diffuse. It goes to an interface, and there we can split the charges. And after that, the charges are transported either in the one type of semiconductor or in the other type of semiconductor. And you can imagine these domains we are talking about have to be very well defined. They can't be too large. Typically, we speak about 10 or tens of nanometer domains. And the arrangement of these domains has to be such that we get a complete percolation from one electrode to the other electrode. So this is completely different to any other type of photovoltaics, where we always have semiconductors of one type, never two type, and this is also this microstructure issue, which is still challenging the whole community. So where are you affected by microstructure? So every one of you who ever manufactured or made a solar cell, you always start with the ink, and even at the state of formulating an ink, you can see various things. You can have a very nice ink, then you take the wrong solvent, and you might get an aggregation already inside the ink. You take again another solvent, and then you might have a gelation, which means your product is totally insoluble in this. So this is the first stage where you have to identify, are you going for a solution or kind of pre-altered solution. Then you go to the printing step, and the printing step is actually the very easy part. Printing step just means you deposit a liquid film on a substrate. That's trivial. The technology is very major. After the printing, you go to the drying step. And the drying step, again, is extremely complicated because in the drying step, you bring in the kinetics of crystallization and the kinetics of drying. And you have this permanent battle between thermodynamic and stable microstructures and the kinetics, which can cause, because of fast or delayed crystallization, very different or unstable microstructures. So that is something we usually don't know. Something is happening from here to here, and then you have to finish a device, you have to measure IV curves, and you have to measure the efficiency, and only then you will recognize, well, did I take the right ink? Did I take the right drying? And then I will get an efficient solar cell. And you see here one of these simulations, what can happen if you mix your two semiconductors and you do not have aggregation, and you have small current generation. If you get very coarse and a large phase separation, well, then you might get better current. And if you go even larger phase separations, then the current is breaking down. And then you are going in loops. Yeah? So you see, well, I have two intimate microstructure, I have to change the solvents, I have to change the drying. So you're permanently optimizing around this change. And this is still done by trial and error, but we are still not able to predict what is the right one. Which materials are used? The first generation was actually materials which came from the OLED business, from the PPV class, which came along from Höchst at that time. The second generation was again PPV, slightly smarter here on the side change. Then there was P2HD, which is still the fruit fly in photovoltaics. Efficiency of P2HD went up to 6, almost 7% by today. And then we had this generation of push-pull polymers, and they developed along like crazily fast, and we have now thousands of structures, and we have so many, so fast publication of the structures that for none of these, actually, any group has enough time to go into the detail and resolve the problems which are related with these structures. So on the one hand, this is beautiful because we have many exciting structures. On the other hand, we have to be aware that probably the best possible structure already was published, but we couldn't see it because we didn't have enough time to spend with it. So let me make a brief summary here on this material challenge we have. On the one hand, synthesis has made fantastic progress over the last years in terms of material efficiency relation. And the people doing synthesis are becoming better and better to design the molecules to get very good efficiencies. On the other hand, we probably have seen more than 100,000 semiconductors published. And if you just say organic semiconductors without photovoltaics, including molecules, it might be 1 million of structures published. If you look to the industry today, the organic photovoltaic industry, they are relying on 4 semiconductors. 2 of them are fullerenes, actually 1 of them, or 2 of them are fullerene mix, and the other 2 are polymers. So out of 100,000 polymers, just 2 or 3 are really in industrial use, and this over the last 10 years. So we are missing something, and this means many of these very promising high-performance materials, from the first-time report that there are beautiful efficiencies to the industrial scale-up, there are so many pitfalls and things to develop that we are losing a lot of materials. And I'm going to try to tell you today that most of the things have to do with the microstructure. Okay, so the second interesting thing is, if you just look to the publications, organic PV publications, they usually are all on efficiency. Yeah? So the people really are focused on efficiency. Very interesting, perovskite PV, already by today, after 5 years on development, they report efficiency and frequently lifetime. So lifetime is an issue in perovskite. After 5 years of development, lifetime is much more of an issue than it is still in OPV. And if you go to publications about silicon, most of the publications are just on reliability, lifetime, and sustainability. So the number of publications on lifetime kind of reflect how major technology is. And this means on organic PV, this lifetime and reliability is a major issue we have to address much better than we did in the past. What do I mean with lifetime and reliability? I mean the degradation mechanisms, and there are many degradation mechanisms. There's photochemical reactions, you can break a bond. There's photooxidation, if there's a little bit of oxygen and water. You can have a backbone braiding or a scission. You have the interface layers. Again, most of the times it's humidity or water, which can cause degradation of your interface layers. You can have impurities, which are causing immediate degradation. And you can also have morphological changes. And what I'm talking is these morphological changes. So where we have either disordered structures or aggregated structures, and these structures can change their aggregation state over the time. One of the first observations we had, which had to do with degradation and microstructure, came along from Thomas Heumüller during his thesis. And he observed when he took different polymers here, this is P2HD, this is a polycarbazole, and this is a bridge by thiophene, at that time synthesized by Konarka. He did observe that depending on the fullerene he's using, 60, 70 versus 60, he could see within hours, tens of hours under one sun, a dramatic breakdown in the photocurrent. So we investigated this in very much detail, and we figured out that in these materials, a main mechanism was coming from a chemical reaction of fullerenes, and fullerenes can, under light and charge generation, dimerize, and these dimers are acting as can act as local electronic traps in the bulk. And this dimerization was causing this burn-in because this reaction took over a longer time and were depending on the microstructure of the fullerenes. In microstructure of the fullerenes, we observed that when you have a highly crystalline fullerene, this fullerene crystallites, dimerization is very slow and delayed. But when you go to the amorphous regimes where the fullerenes are aggregated but not crystalline, like these aggregated fullerenes, they easily undergo dimerization, and then you get these defects in the electronic structure, in the electronic transport. So that was the first time we realized it's interesting. So crystalline regimes are always good, but when you look to the amorphous regimes, then you may get undesired effects. That was the starting point, and a little afterwards we had another experience which came along thanks to this fantastic material which was synthesized in Henry's group. We found on some of these batches, under specific conditions, we found another effect which was amazing, and this was a similar burn-in effect. Yeah, you would see here over, in this case it was a long time, like thousands of hours. Under light. So that was something we still thought it could be dimerization. But then we looked also to the degradation of these layers here with these polymers, with C70, in the dark. And for some of these fractions, we could see that in the dark we had a drop in this JSC, this burn-in a glove box, under nitrogen, in the dark, under best possible conditions, no heating of 10, 20, or 30% within 24 hours. And that is something which we did not expect. So we were actually really surprised that in a bulk heterojunction we can have in the dark an intrinsic unstable state. And as usually you get when you have these observations, you don't understand, then you get fascinated. Yeah? And we try to figure out what it is. And the first thing we thought is that we are breaking up our crystallites. So we took the GVAX and the GSAX images the first thing we observed is that there is here between the fresh, this is the UV vis change and the surface wetting angle. So in the surface composition, we did not have any difference. And on the GVAX, GSAX, fabricated and degraded, we did not see any difference at all. You can see here the red and the black line, so this is the fresh one and the degraded one. So the crystalline structure was not affected at all. Interesting. So if the crystalline structure is not the reason, then it has, of course, to be the more amorphous regime. And what we observed was actually very insightful. Optical measurements, photoluminescence and electroluminescence measurements. And you can see here the electroluminescence and photoluminescence of pristine fullerene, and in this case, the PC11 polymer. And after degradation, we could see that the degraded system had a stronger emission, which were indicative for the pristine phases, more of the polymer, but also more of the fullerene. So obviously we had a phase separation in here. And this phase separation, as the crystalline regimes cannot change, again, must have come from the amorphous regimes. So there's a driving force which is causing to split up the fullerene from a polymer in these systems, and actually we found many, many more systems as well. Actually, I think we more or less observe this in all of the systems, sometimes to a large extent, sometimes to a smaller extent. So there's a driving force which is causing this fullerene to split from the polymer. And that driving force got us triggered, because that is something we believe we have to predict in order to make sure we can engineer stable systems. So how do you predict miscibility? How do you predict the driving force for phase separation from two components? And we went back to the very old theory, actually. This is the Flory theory for polymers, and Flory developed the theory for solid solutions, which you can apply either to polymer systems, dilute solutions, or even to polymer systems in the solid state mixed with small molecules. And you have two parts to predict miscibility, and the one is the entropic part and the other one is the enthalpic part. So the entropy and the enthalpy. And the entropy part is the very simple part. What you do is you take such a lattice and then you say, well, this might be my fullerenes, and the fullerenes can occupy any space. And then you have to place in your polymer, and the polymer, depending on whether it's a very rigid polymer or very flexible polymer, you have more or less possible conformations. Yeah? And the entropy then is very easily calculated. You have here the free volume of one unit cell. So you have the volume fraction of in that case, let's say the polymer over the length of the polymer, and you have here the volume fraction over the fullerene, over the length of the fullerene, which is 1 in that case, and then you get the entropy. And if you have a very stiff polymer or a more flexible polymer, the number of conformations is changing, and you can correct this here by a prefactor. So this is how you would call the driving force for mixing by entropy. And entropy is always causing a mixing if you go to smaller molecules. Yeah? You see here the difference between the systems which have a chain length of, let me say, 100 and then 100 and 1,000, and you see the entropy for mixing is going down dramatically. So smaller systems have a higher, so small molecule systems have a higher driving force for mixing. This is the entropic part. That's the easy part. The enthalpic part for mixing is much more complicated. If you look to the equation here, you have similar terms again from the entropy part, and then you have this interaction parameter. And the interaction parameter is giving you the measure of interaction between one molecule with the other molecule. This interaction parameter is directly related also to the Hildebrand energy of evaporating materials, and you can calculate this interaction parameter if you know the single Hansen or Hildebrand parameters of molecule A with the molecule B. And usually these parameters are very difficult to access. I'm going to show you later on how we access them, over which theory, but that is one of the challenges to access these parameters, and to calculate these parameters is extremely difficult. So entropic part and the enthalpic part, and these two give the mixing enthalpy. And if this mixing enthalpy is positive, you have the mixing. If it's negative, you would have mixing. Positive means unstable microstructures, negative means stable microstructures, and in between you have the spinodal demixing. So what Jose was developing, and he's a PhD student close to finishing, was a software algorithm to calculate and predict the enthalpy of mixing, these interaction parameters, and we put it into relation with the entropic mixing. And what we have here, this is the part how we calculate the entropic mixing, or the spinodal mixing. And just to go back, this is this part, and actually you do not have to know much about the molecule, just the molecular weight distribution. Yeah? And whether the polymer is very stiff or it's less stiff. So this is straightforward to calculate. We make a simple molecular optimization. You can do this in DFT. We get the free volume, and we can calculate spinodal demixing. The enthalpic part is more difficult because you need this parameter. And this parameter you usually do not get out from DFT. You would have to do molecular dynamics because you need to know how the molecules are interacting with each other. So no way we would do molecular dynamics because this takes forever. So we decided to take a specific way of DFT calculations, and this DFT calculations is called COSMO, and it's calculating the surface charge distribution on a molecule. This is known to be very precise for polar and hydrogen forces, but it is also known to not be able to predict dispersive forces. The mixing enthalpy is mainly determined by the dispersive forces. So we had a problem. How do we come from this surface distribution to the dispersive parts of the mixing enthalpy? And you cannot do this by quantum chemical calculations. So we got the advice to look into machine learning and neural networks. And we took the surface charge distribution here, and we took a Taylor series, and then we trained a neural network analyzer. And you only can do this if you know, on the one hand, you have to know the interaction parameter experimentally. And we had 15, 16 fullerenes we could use to train the software. And on the other hand, we trained the software with the surface charge distribution, and we did this over and over again. And after some time, we got a fantastic fit for the interaction parameters between polymers and fullerenes. And once we had this, once the neural network analyzer was trained, we were able to predict the interaction parameter for any new fullerene. And with this, we now had the entropic part and the enthalpic part, and we combined these two into a figure of merit. And this figure of merit is supposed to predict the relative miscibility and therefore also stability with each other as a function of the mixing ratio. I'm explaining this in a little more detail. What you see here is again the calculations we were doing for PC11 and many different fullerenes. And you see here the distribution for the figure of merit. And for the figure of merit, you see here the enthalpic part divided by the spinodal part. We have to do this because both of them have a free volume, and the free volume is difficult to give in fixed numbers. But when we take the ratio, we get a number which is independent of the free volume. So therefore, these values are very comparative. And you can go through this plot, and you see the higher you go up. So the higher you go up, the larger the difference here in the enthalpy is, and the less miscible systems are. The more you go down, the smaller this part, the larger the entropy is. And this is the demixing part, and this is the mixing part. And this allows you immediately to predict whether the one structure might be stable over the other structure, whether it's miscible or not miscible. Keep in mind, this is always supposed when you are in the thermodynamic equilibrium. We are screening out any entropy, any kinetics out of that. Okay, so what are the consequences? If you believe that this is the right picture explaining burn-in, then the first thing to address is we would think that the mixing ratio between polymer and fullerenes is more or less independent of the crystallinity, but more depending on the miscibility of these two systems. And we analyzed a couple of data from the literature, very old polymers, but also some of the new polymers. And you can see this is pretty good fitting. For these systems which are known to have a 1:3, 1:4 mixing ratio, these are usually the systems which have a fairly good miscibility. And for the systems where we have 1:1 or 1:2 ratios, these are the systems we calculated to have a low miscibility, which is also slightly different to what the people still believe from the literature, that the crystallinity is addressing this. There is also, you may notice, a similarity between crystallinity and miscibility. What is in between these two is, of course, the kinetics. If a system is crystallizing faster, then you always can go into a metastable microstructure, but in the moment you would apply higher temperatures, thermodynamics is always winning. So the second prediction is, if that is true, then it would be the case that people, when they process solar cells, in many times they process it in a metastable microstructure. Not the most stable, but it's always a metastable microstructure. It's an in-between. And again, we have been able to prove this beautifully by this polymer and fullerene. And just look here at the thermal degradation. And you can see at the 35 degrees, it takes a long time, but then it gets stable. And you would think, wow, now I'm stable. You increase the temperature, you go to 60 degrees, it's going down again and becoming stable. Do you think we are stable now? No. You can go to 85 degrees and it's a very sharp and fast drop, and then it's getting stable. So this means this composite was processed in a way that you have a metastability, and the metastability depends on many things, but you're never in the stable state. The second very interesting consequence of this is, if that is true, what is causing the burn-in, then degradation under light and degradation under temperature would have to be identical, because it's always the same instability, metastability of the materials. So look at these curves. We have here the polymer-fullerene ratio mixture. This is thermal aging for 2 hours, and you can see we have the burn-in. And after this, we go into light aging for 500 hours. There is no change. We can reverse and flip around the sequence. Now we do the light aging before. We have the burn-in. Then we go to thermal aging, no changes. Yeah? So this means whenever we see these instabilities, these burn-in effects, this thermal aging, this light aging, at least for the systems we looked at, it is a microstructure instability which is coming or deriving from this intrinsic demixing in these materials. So let me conclude this part. And the one message is instability under inert conditions. You notice that we do not have any oxygen or hydrogen or water humidity in there. Burn-in is caused many times, most of the times, by the fact that we are processing these polymer solar cells in microstructures which may have a local minima instability, but not a global maxima. And once you start stressing the solar cells by light, by temperature, by current, you always go, thermodynamics is always going towards a more global minima, and these minima frequently are not the one which have the highest efficiency. But many times we figure out that the microstructure which gives the highest efficiency is not a global minima, but it's just a local minima which is metastable. The second one, we figured out this parameter, the interaction parameter, is extremely valuable. If we would know this for all the systems and the solvents, we could make a very good, probably much better prediction of stable microstructures as we can do today. Keep in mind the system we can expand. So far we just calculated polymers and fullerenes. We can do the same with the solvents. We can do the same with the inks. We can calculate what is the interaction parameter during the drying. So we can mimic the microstructure formation over all stages which we are doing. So that is actually, we believe, one of the key parameters to access. So the second or third observation is that parameter, at least for the fullerenes, we are able to calculate by a neural network analyzer, by machine learning coder, which is very interesting because you cannot calculate this parameter ab initio because you would have to need the detailed microstructure, which you never know. Even from molecular dynamics, you wouldn't figure this out in larger samples. So that is interesting. Neural networks can calculate parameters which you otherwise cannot access if they are properly trained. The question is, the proper training is an issue because for any new type of molecules or class, we would have to train these softwares typically by hundreds or even better thousands of different molecules. Yeah? So the question is then, for this training, how long does it take to experimentally determine one of these parameters and how many can we do there? So the next section, I'm going to tell a little bit about this interaction parameter. How do you determine this experimentally? This is Stefan, and Stefan is making his PhD on the experimental determination of this interaction parameter. This experimental determination is following over the concept from Hansen, and this is the Hansen solubility theory. So this is the interaction parameter, and you see here, this is the Hildebrand energy of molecule A and the Hildebrand energy of molecule B. So it's the Hildebrand energy. This is, if you have a pristine system like a solvent, you measure this Hildebrand energy by simple evaporation. Yeah, it's the diffusion energy you need there. For polymers or fullerenes, you can't do this because you destroy the structures. So the concept you need there is the concept of the solubility theory, and this was developed by Hansen, and Hansen took the Hildebrand parameter here, the cohesive energy, and he split it up into dispersive and polar and a hydrogen part. And Hansen's expectation was, let's define a solubility limit in something like milligrams per milliliter, let's say 10 milligrams per milliliter. And then let us test tens or hundreds of different solvents and identify whether the polymer is getting dissolved or not dissolved. This is looking then like this. Yeah? So you take your polymer and you take many different solvents, typically 30, 40 solvents, and then you figure out whether your system is dissolved or not dissolved. So that is the bottleneck. You need so many solvents, and then you determine the solubility, and then you draw this Hansen points, and every point which is soluble you mark as blue, and every point which is insoluble you mark as red, and then Hansen predicts you can make a sphere around, and everything which is inside the sphere is a solvent, everything which is outside the sphere is a non-solvent, and this is how you determine the Hansen parameters, and from this you add these Hansen parameters, you get the Hildebrand, and then you have the interaction parameters. So that is fairly complicated, and you need lots of materials. You need grams in order to do this test. Doesn't work. So Stefan was developing an algorithm on a robot. And on this robot, this is a simple pipettier robot which can just do mixing, shaking, centrifugation, and it's done fully automated. He invented an algorithm how to measure this Hansen solubility just by optics. And the key step was there to make oversaturated solutions, which we went to centrifugation. We diluted them. We had a master curve of the absorption, and then we only had to measure the absorption in a plate reader, compare it to the master curve, and we knew the milligram per milliliter which are stored inside this. So we implemented this algorithm on a robot, and if you compare now doing it by hand and doing it by the robot, we are probably 50 times faster. We can do very complex solvent system. The material consumption went down from more than several grams to less than 50 milligrams. The last test we could do with the 30 milligrams, and the time was much faster. Now it takes us an hour or hours to determine the Hansen parameters, and if you do it by hand, it takes 3 days. So we can do many of these determinations now in parallel, and this is what we are starting. And with this, we are going to train new neural networks now, not only for fullerenes, but also for polymers, for small molecules, and so on. And this we are doing here in cooperation with Benjamin and Ellen Gasbour from Harvard University, who are the experts in machine learning. So they are supporting us here with the software. So how far are we? We started with small molecules because we have a database of 10,000 of these small molecules. They are mainly solvents. Yeah? So in the later stage, we want to go to polymers, conjugated polymers, fullerenes, non-fullerene acceptors, whatever we can get. But this is available by now. So for this, we have experimental data of the interaction parameter, solubility parameter. We started to make the DFT optimization of the structure. Then we calculate the sigma moments. We get the fingerprint of the structure. With this, we go into the machine learning. We train the network, and then we get the Hansen parameters. The difficulty is here. Usually when you make a full DFT optimization of the structure, it takes half an hour. So we are now managed to get here the fingerprint, just the 2D pick structures, which takes us a minute per optimization. So we actually, with a batch process, we could run thousands of smaller molecules through this optimization. And within days, we got the Hansen parameters for the thousands of molecules. So you may ask, how good is this? We split this in two parts. We trained the machine learning with the 5,000 molecules, and then we verified the precision of these results on the other 5,000 molecules. And you see here this a result when we have this 1 minute, 2 minute optimization of the architecture, and you see the variation in these three Hansen parameters, and you compare these variations of 0.5 or 1 dpi with the error in the experimental determination, and the computer algorithm is already better as the experimental determination. So this means it's trained perfectly, and we can predict any new solvent you might give us. We can give you the Hansen solubility parameters within minutes back. So, and the next point is, of course, to extend this to the small molecules and polymers. So, short summary also here. These Hansen parameters and the interaction parameter, it's very important, yeah, fundamentally important, and it's beautiful. We can measure it by a robot with 30 milligrams for a material which is a fairly reasonable size. The neural network analyzers allows us to ab initio predict parameters which you cannot calculate otherwise. Yeah, so these two actually are fantastic fantastic combination, a robot and a neural network analyzer, because right now we don't think there are any limits in predicting any other material property. So for the solubility, we could show it. But of course, there are much more interesting questions. And the question is now, can we do the same for efficiency? Or can we do the same for stability? And to really start predicting efficiency and stability rather than guessing about this. So this is now the major project. And I'm concluding the efforts for the efficiency and stability. We have to make devices. For the Hansen parameters, we could work on just materials. The devices are much more complicated, so we are putting up now a robot-based device engineering setup. And this is this work from Toby, and you see here multiple glove boxes, and these glove boxes have many robots, and these robots are supposed to become independently able to make full solar cells or any other device. The idea we are following there, this glove box is divided in different sections. We have the material and solution sections, we have the thin film section, we have the characterization section, and then there's all the data handling, storage, the outreach to the machine learning, going back to the ab initio design of new materials, going back to work with chemistry who make then the better materials based on this result and feeding this in again into this loop. And the stage here is, you see here what we are doing in the material selection, and it's fairly easy. So we are just doing pipetteering, we are doing weighting in solutions, we are doing centrifugation, we are doing mixing, we are doing heating. So these are all the things a robot can do fairly easily. On the thin film section, it's a little more complicated. So we have programmed the robots now to do simple spin coating. We are programmed to do doctor plating. The next is we are going for the aerosol jet printing, which can do very fine and high resolution, and we are going for the spray coating. So these are the methods how we will deposit then all the different semiconductors with the different robots. On the characterization, all the optics is there on the large scale. You see here one of the setup this is a plate with 96 devices. Each device has 6 solar cells. So this is a plate where we have like 500 different solar cells. We have a solar simulator. We can measure this in parallel. And we are adding also more complex transient analysis to this robot to not only measure the device performance or efficiency, but also like a lifetime or mobility. The more difficult part is the lifetime, because the lifetime has 2 aspects, and the one is statistics. And if you want to do a lifetime, you have to make many of the devices. Never trust a single lifetime event. So we expanded our lifetime, statistical lifetime testing. You see here single chambers with different light sources. Each of these chambers can hold up to 2 of these holders. Each of these holders has 9 substrates, like roughly 50 cells. And we have many of these, so by today we are able to test more than 2,000 devices in parallel, and that's actually necessary. If you imagine you have a robot who can make 1,000 devices a day. Yeah? What is important is we can vary the spectrum, we can vary the temperature, and we can vary the atmosphere. So some of these chambers have a controlled atmosphere, not only nitrogen, but also oxygen or humidity. And why is this so important? Control of the spectrum is essential because we distinguish between resonant absorption and high energetic absorption. Many times this part in the UV is causing a separate degradation, which we do not want to see here when we look for the microstructure. And the second part is, this is what I meant with statistics. So this is one of these examples of in situ IV degradation curves. And the beautiful thing is, for these people who are in solar cells, when you see such an evolution of the curves from here to here, the isospectic point and the fill factor break-in, you do not even need to simulate the device. You just look at it and you know perfectly what had happened. And the hope is that we can train actually some of these machine learning imaging recorders to just, instead of taking real tables, just to take such an image and then predict the type of the failure. So this is statistical testing, and then there is accelerated lifetime testing. You don't always want to wait for 1,000 hours if you are quick. So for this accelerated lifetime testing, we have developed specific chambers where we can apply up to 700 suns. So 700 suns means that you can do your 1,000-hour lifetime testing in roughly 1.5 hours. The difficulty is when you go to 700 suns is you easily get temperatures like 1,000 degrees, even higher. And organic solar cells don't like too much this 1000 degrees. So the cooling is important, and we managed to be able to degrade under hundreds of suns, but still keep the temperature even at 0 degree if it's required. So the temperature control is here extremely important. And again, we have to control here. We can control the atmosphere here. So this is then for the accelerated lifetime testing. You take all of this together and you have to put it into data handling. We are creating databases now. In this database, we will open out to the external part and other research labs. And the hope is, and this is the long-term vision we have, to really initiate this materials genome site for organic and perovskite photovoltaics, where, for instance, labs like our lab in Erlangen is doing a lot of hardware testing because we have robots, but we are linked to many other labs, and they might have another specific investigation method. Think about that as synchrotron doing X-ray studies, but also think about many times here labs coming from the chemistry who are supplying just materials or who want to have the materials characterized by these efforts here, which hopefully is going to spread out over many of the significant key labs worldwide. Okay, so with this short summary in between, and then I have the conclusions. After 2 years of development on this Glovebox robot system, I told you, and approximately 1 million lines of code we had to write, we are close to actually make full devices. Yeah? Close means we thought we could get full devices by this year, but Toby is believing it might be rather 2018. Nominally, the Glovebox and the robot you saw would be able to do up to 5,000 devices a day. Let's see if this is true, but even if you can do hundreds of devices in a day, you will get so many solar cells that it's obvious there's no way you can analyze it. So to go after this materials genome, machine learning, neural network analysis is essential because we are generating more data than we can analyze. So therefore, a robot, in our point of view, always has to come together with the right software to allow you this automatized improvement of the next generation of these materials. And the interesting thing is, in this case, we hope that we can address lifetime and stability in parallel to efficiency and really go towards the next generation by this materials genome. And what we are looking now is groups who are interested to join this adventure on the materials genome, because it's obvious that every group has to stay on this expertise. Our expertise is on the testing on the robot. We have cooperations on the machine learning. We are getting more cooperations on the chemistry, and if you are able to link all of this, there might be a fairly good chance to really make the next step in this exciting journey. Good. So let me conclude. On the OPV, the biggest challenge, and actually in perovskite, it's not so different. And you can guess the reason for this is it has to do with this low temperature solution processing. Low temperatures always bear the danger of going into metastabilities, which people who are doing crystalline silicon, which is processed at 1100, 1200 degrees, never will see. Because if you process at 1200 degrees, you are by definition in a stable state, not a metastable state. So the solution processing is really bringing in this metastability in the photovoltaics, which we haven't seen in other systems before. So microstructure, therefore, we are not disappointed that we are still discussing microstructure 15 years after this APL paper. It's natural because the microstructure is the challenge of this topic. That is new. Machine learning and neural network analyzers, they can help us to identify the hidden parameters which cause all these non-reproducibilities, these instabilities we have seen so far, and which we do not get under control. Disadvantage is we need statistics. We have to train them. We need statistics. But on the other hand, I believe there's a very good chance that over the time this will give us a significant progress. And the other advantage is these network analyzer softwares, they are capable of handling hundreds of thousands of materials, so they have the right volume to do this. Well, and the last point is on the robots. I guess this is a necessity to couple robots to these network analyzers, because otherwise there's no way to ever get into these large numbers here. But on the other hand, what is also a major advantage of these robots, which we saw already by now, is this incredible good reproducibility. You see this on the lifetime, we saw it on the Hansen parameters. The robots don't have a good day or a bad day, which many other of the process engineers do have. And actually this quality of data is another major advantage, which we hope to see on this journey. So with this, I'm finished, and I'll thank you for the attention, and again, Henry, for the nice invitation.
Oh, thank you very much. I don't know what you guys think. I was pretty much impressed. Wow, if we could test 5,000 devices in a day, wow. We don't need so many device people, right? We need more chemists. Okay, any question? Question from OPV people? Don't feel shy, asking questions. People who are.
But I can relax all the people. So the robot is actually also threatening all my students.
Okay.
Because they are getting afraid. Jesus, can I make a PhD thesis if there's a robot? So my answer is, it's a different way. The robot will enable the students to make much better PhD theses because you only make experiments which are reproducible, you can rely on. And the science is starting actually after you get the data, and you don't spend so much time. At least this is what I tell the students. Not all of them would believe me, but I'm pretty sure it's a good thing. It should be helpful.
Okay, any student worry? Okay, ask question. Okay.
Thanks. Sorry, can I ask a question? I'm not an OPV student, or my research is not really that as now, but could you outline how or why is it that ab initio methods cannot be used to calculate the interaction parameter?
Yep. The reason why we are struggling is that for this interaction parameter, you need to know the precise arrangement of the molecules in the bulk ensemble. And the fastest and the largest scale methods we are currently looking at, they can handle materials composites up to 50,000 atoms. And then they find some minima, but you're never sure whether this is also the right minima. And this means for these 50,000 atoms, our supercomputers are currently calculating in the order of weeks. So like for one material combination, which is very important, we might be able to do such an arrangement and make the precise optimization of the microstructure, and then you can calculate the interaction parameter. If you want to do this for tens or hundreds of materials, then at least the current generation of supercomputers is not capable.
Any other question? I have one question. And one of the earlier slides you mentioned about PCBM, fullerene. The amorphous region is more sensitive to the dimerization, but the crystalline region is not. Why is that?
We think because of the rotational freedom of PC60BM.
Oh, okay.
So fullerene's C60 itself can rotate around the axis, C70 around the directive axis. It's a speculation. We don't have a proof, but what we thought is if you look to the crystal structure of PC61, it's actually fairly complicated. It has an octahedral superlattice, and in this, not all rotations are fully allowed. So we thought one of the reasons why it's so much slower is because the confinement in the crystals is higher than in the aggregated regimes, where we would not have a confinement of the rotation.
So the molecules have to, take certain positions, orientations to do the reaction.
Yeah.
Okay, that's very interesting. So I guess if we could make a more crystalline structure, less amorphous region, and that will help the stability, right?
Yeah, absolutely. So this is one of the ideas. If you think about this consequence, so let's make it more crystalline. Then let's separate the P and the N domains. Yeah, so we are ending up in the PN junction of silicon then. It's the same concept, right? So ideally we would like to have a P layer and N layer. They all should be 100% crystalline. So this is then where we sometimes we call this liquid silicon. This would be the perfect structure. Yeah? But as long as we are limited by this exciton diffusion length, this will be very difficult.
Yeah, if we have a pure two-phase morphology, that will have less of this problem, but that's difficult to achieve.
Whether it's so efficient, then yeah. Mm-hmm. Yeah.
Question?
So I'm not an OPV specialist either, but I'm working in flexible electronics, and OPV has the main advantage to use organic materials, which means flexible materials. Do you think OPV will be mainly focused on flexible devices instead of silicon and perovskite will be focused for bulk and rigid solar cells?
Yeah. Flexible is one way to look at it. There's another word I love to use, and this is integrated. So I guess one of the strengths is with organics is the integration into, and this can be any irregular surface, a curved surface. It can be fabrics, it can be textiles, it can be glass. So that is very easily possible because you have a low temperature process, so you can directly produce on any other surface without damaging the surfaces. So the integratability of generically low temperature processes is just fantastic. For silicon, it would be very difficult because you only would be able to start integration there on the level of a wafer, and then you have to make a pick and place. Or gallium arsenide, you can make small chips, and then you have to make a pick and place. But OPV has the advantage that you can directly produce on top, and I guess this is a major advantage. Whether you would do this on a rigid surface or on a curved surface or three-dimensional or flexible surface, all of this is good, but producing directly on top is one of the advantages.
Any question from students from my group? Guys do not like to ask questions. That's not good. Okay, someone speak up.
So I hope the robot didn't scare off too many people.
Yeah, Gongye.
Okay, so at one of your slides, you conclude that the morphological instability was the main reason for the burn-in of PC11 and PC71BM. But you reversed the light soaking and the thermal heating in one of your slides and showed that eventually they went to the same global minimum. But the burn-in rate was different between these two processes. Was it simply because of the heat associated within these two processes, or is there's anything to do with dimerization in these two processes?
Yeah, we are pretty sure that we can exclude dimerization there because we took C70 specifically of this purpose, and there should be less than 1% of dimerization on the impacting on the performance. So the dimerization is of. I mean, your question is addressing a very good point, yeah, because we are not able to fully answer this. We believe this has to do with the excess energy being dissipated into the lattice. I mean, it is obvious that you have light and thermal and heat dissipating energy into the lattice. And it's also obvious that you only will see an effect if you go over either primary or secondary glass temperature in either of the systems, either the polymer or the fullerene, which is, I think the one is here at 67, 70, depending on the molecular weight, and the fullerene somewhere at 100. So these are the 2 points. You are dissipating energy, and then either of these two is softening, and then you get diffusion. So I mean, I guess it's obvious that by when you have photons coming in, the dissipation of the heat is much less, or the coupling into phonons is much less than thermal heating. So I guess this is the reason that we see it's so much more accelerated. Yeah. We haven't tested what is happening beyond the 85, but so we are still not sure that it's really a global minimum, but we believe it's fairly close to the global minimum.
Any other question? Okay, if no other question, let join me thanking Professor Brabec again.
Thank you.